Hello, welcome to Hampshire Piano. I'm Craig, and I have something interesting to share with you today. What this is a homemade reconstruction of a sales room demonstration prop that was put out by the Mason and Hamlin Piano Company. Oh, gosh, I first saw them in the 80s. They were old then. So they could have been put out in the 50s, 60s. But what they are is, well, how simple can an object get? It's a tuning fork, a 440 tuning fork, and it's mounted into a piece of soundboard spruce. For the record, soundboard spruce is quarter sawn, which means that the little grains go up and down. And that means that the wood is the strongest it can be in this flexing pattern. So what this object demonstrates is the effect of straining an acoustic body to optimize its response to an input. And rather than talk about it a whole lot more, I will try and in here it's got a nice steady tone. The body does respond to the fork. So but if you strain the body, there's a marked effect. The signal becomes noticeably louder. It's a little hard to hold it at just the right spot because it takes a bit of strain. But this object, in a nutshell, encompasses the goal of everything they do to a piano soundboard in the process of its manufacture. And I want to talk a little bit about the physics of what's going on in this, but first off, I just wanted to show the natural phenomenon that's behind all the techniques that go into optimizing it. And that's just when you bend something, it becomes more acoustically responsive. I'm sure this technique is used in a number of instruments, but for pianos, it's crucial to what they are. So, I generally wouldn't begin with the conclusion to a thought before I express the thought itself. But I think I had best in this situation so that it's clear where I'm going with my next ramble, um, so that you might want to follow me. The conclusion to this thought is fundamental resonant frequency. And that is a property that all objects have. But because we're talking about musical instruments, resonance and fundamental resonance is kind of the focus of the whole study. And if you've ever seen a luthier holding up a piece of wood and going, what they're really trying to do is to elicit the wood's fundamental frequency, and that would be the object bending as a whole this way and that way. But things vibrate in little subdivisions too, so they want to see if they can't hear what kind of higher frequencies it might put out. If you grab a piece of wood around the quarter point and tap it at the middle, you'll get pretty much its fundamental frequency. This is basically what all luthiers and piano guys are trying to control in their final product, is the resonant frequencies of the body. The guitar wants one thing, pianos want another, but it's the same characteristic that's being examined. Now, the physics behind all that are covered in a study known as mechanical impedance. And in a nutshell, mechanical impedance is the study of how an object responds to vibration. And that means vibration of different intensities, vibration of different frequencies especially, and vibration applied to the whole body, and vibration applied to points. In a structural engineering capacity, I would suggest taking a look at the footage of the Tacoma Narrows Bridge disaster. That shows where mechanical impedance gets out of control. Because what the study of mechanical impedance is what frequency and where on a body or as a body as a whole does the object have its lowest resistance. Generally on something like this, the lowest resistance will be in the middle, of course. But like a bridge, there'll be a frequency at which you can get it bouncing. And that is point, and frequency is what they would call the point of lowest mechanical impedance. Now when it comes to bridges and buildings, imagine this study related to earthquakes. What frequency can a building stand and what frequencies can't it stand? You can see where the whole idea would be to find those points of lowest mechanical impedance and brace them up. Now, in the field of musical instrument making, this study of mechanical impedance gets put to a slightly different purpose. rather than identifying the frequencies that an object is most sensitive to and the spots on it that it's most sensitive to frequencies, and eliminating them, in musical instruments we try to control them and, well, most precisely enhance them so that there's a better response to the instrument, and and not necessarily subserviently control them. An even response in an instrument is really important for a musician to control what they're doing. An instrument that has a weak section that has to be borne into, or a barky section that has to be treated with kid gloves, does nothing but distract a musician from what they're trying to do. And in a piano, you're not dealing with 6 strings, you're dealing with better than 240, so evenness of response is kind of paramount. So that's why this impedance question is so important, because it will come back again and again in the process. I could have just started with fundamental frequency and how to, manipulate that a little bit. That's what this is. I felt we needed a little understanding of where fundamental frequency comes from. And it is just the nature of stuff. This is a wide, thin, long object of rather light material. Spruce is not the heaviest of woods, but because of its physical nature, and I will be getting into this in great detail in the future, it is very, very strong in this direction and this direction compared to its weight. This is like nature's carbon fiber. It's hard to beat. And that's kind of why pretty much all stringed musical instruments use spruce of one form or another as their sound transducing material. And, and why a lot of them use maple as the mount. You just have a perfect balance of dense and solid to light and strong and springy. But because everything has its inherent flexibility, that's where the impedance question of, what frequency does this bounce at most readily, and what frequency gets it moving the most. And here's where we're getting back around to finally where I started. The frequency that makes this thing wobble and respond the most is the fundamental frequency. It is that lowest possible tone. And that tone, like I said, that tone being the tone that the object most readily wants to respond to, would explain why, since we have an actuator that has a fixed pitch, a fixed energy level, a fixed amplitude of motion, every adjustment that can be made has to be made in the resonator. there are a number of things that can be done to raise the fundamental resonant frequency of the resonator. But this object focuses on just the one. And basically that's, if you take an object and bend it and stress it, it becomes stiffer because it's resisting. When it becomes stiffer by bending it, the fundamental resonant frequency of the resonator goes up. That's easy enough to hear. Just bend a little. See? It's not, I would just say, it's not something unfamiliar. It's just that as this demonstrates, when you've raised the stiffness to the point where the lost for words for a second, the mechanical impedance has raised the lowest resonant frequency up to the frequency or a related frequency of the fork. The efficiency of the energy transference went up because the fundamental resonant frequency is the frequency at which energy is most readily transferred at the greatest amplitude between two resonant bodies. What that means in effect is this system can take on just so much energy, and it will filter it, it'll disperse it out through this body at just such an efficient rate. What that amounts to in the end is the fork can only get so loud, and the body can only radiate so much energy to the air as sound, because much of the energy of the fork is being lost in a mismatch between the fundamental resonant frequency and the body. When it is stressed, the fork seems to be able to take on more energy to start, and that energy entering the resonant body creates both more sound and lasts for a longer duration at that amplitude or at a higher amplitude than the unstressed body. That is the effect that impedance matching is all about. And to conclude, I want to run some simple experiments with a decibel meter and see if I can't get some graphic metric on this phenomenon. What I'm going to do is I'm going to hold the device up and strike it, and as I did before, flex to bring out the phenomenon and see if the decibel meter reacts. And secondly, I'm going to strike the device unbound like this and get a tone profile for it, how loud it is, how long the tone lasts, how well the tone lasts, and then I'm going to string up the device with this retainer that I built and strike it and get the alternate tone profile and see if there's not a marked difference in the two full-length tones. So I'm going to be doing this off screen, so that's why I described what I'm going to do. And all you're going to see is the decibel meter, but you'll know what I'm doing. Okay, as I said, first we'll take a look at how it was used in the showroom for the effect. Okay, activate it. And there, as you can see, it starts out with a nice strong tone. When you squeeze it, it jumps up. It's kind of hard to hold there, but when I release it, it jumps back down. Take it back up when you flex it. So, there is a marked increase in volume if I'm using this decibel meter correctly, anyway. Okay, let's take a look at the signature of the unbound system. Okay, well, as you can see, it had an impact of about 69. That's essentially the loudest noise it makes. And it immediately dropped down to about 60 and had a smooth degradation down to about 47. I tried to give it about a 15-second run. So let's try that same thing. On the bound system. I think you'll see the effort of the pursuit is worth it. So. There's our sample. And what you can see is that while it came in a little louder, it didn't have that immediate drop down of about 10 decibels. So the system absorbed all that energy. It's feeding it out at a higher level. There is one little drop there. That's, I guess, at about 12 seconds this thing seems to have a signal degradation. But even with that, at the end, it's still got more energy left in it than the unbound system. So, as best I can tell, that's all attributable to matching the impedance between the actuator and the resonator. So, I guess that's what, as I understand, is meant by impedance matching, and this subject will come up many times as the subject of soundboards progresses. But this is where it starts, this is where it ends, and I want to thank you for hearing me out. Thank you. Bye-bye.